My name is Yessica Peralta. I'm a research engineer working at the Reservoir Geomechanics Research Group at University of Alberta. Today I'm going to talk about this poster. The title is Thermo-hydro-mechanical coupling simulation platform for an isotropic porous media validation. This poster has four main parts: the background, the purpose, methodology, and results. Let's start with the background. Thermo-hydro-mechanical coupling, or THM, describes how heat, fluids, and mechanical stresses interact underground. These interactions are key to understand the stability and performance of subsurface systems. For example, in geothermal energy, THM explains how heat extraction changes rock properties like permeability and porosity, helping optimize fracture networks and predict long-term performance. In nuclear waste repositories, THM governs stress redistribution, fracture growth, and chemical reactions that affect containment over thousands of years. For underground storage, whether hydrocarbon, carbon dioxide, or compressed air, the temperature cycles during injection and withdrawal can weaken rock stability and increase leakage risks. And beyond energy, THM processes are critical in mining, tunneling, permafrost stabilization, and artificial ground freezing. In short, THM coupling provides the foundation for designing safer, more efficient, and sustainable subsurface projects. So let's talk about the purpose. The purpose of developing a thermo-hydromechanical simulation platform for anisotropic porous media is to create a comprehensive, accurate, and efficient tool to study how heat, fluids, and stresses interact in the rocks that behave differently depending on direction. This platform integrates multiple physical processes into a single framework and accurately captures an isotropic properties like permeability, stiffness, and thermal conductivity that vary with orientation. It enhances predictive capability and risk management by forecasting deformation, fracture growth, pressure buildup, and even potential mechanical failure, ultimately improving safety. It also helps optimize design and operations, such as injection and production schemes, to increase efficiency while reducing risks. Finally, this simulation platform provides a flexible, standardized tool to support research, innovation, and hypothesis testing in geomechanics and reservoir engineering. Now let's talk about the methodology of this work. In our study, we implemented the coupling between fluid flow, heat transfer, and geomechanics using the fixed stress split sequential method. The workflow is controlled by RGRG coupling platform, which was written by using C++ language. This code links CFG, which is the software used for solving the equation for thermal and flow processes, with Itasca products such as Flex 3D or 3DEC, which is the software used to solve the mechanical deformation. Here, how is the sequence work? First, CMG solves the thermal and hydraulic problem under the assumption of fixed total stress. Once These conversions, the pore pressure and temperature are passed to Flux 3D. At this point, the RGRG platform calculates the stress increments caused by pressure and temperature changes using the generalized biotensor. This is important because in anisotropic materials, pore pressure can also induce shear stresses, not just hydrostatic effects. These stress increments are applied in Flux 3D, which then computes the mechanical response of the reservoir under drained conditions. After reaching the equilibrium, the updated stress and strain tensors are used to calculate the new porosity, pore compressibility, and thermal expansion coefficients. These corrected values are sent back to CMG, ensuring that the next flow steps accounts for geomechanical effects. The process repeats in short sequential cycles, with time steps chosen small enough that stress changes can be considered instantaneous compared to fluid diffusion. This guarantees both accuracy in capturing geomechanical feedbacks and conservation of fluid mass. This iterative exchange between CMG and Flux 3D continues until the end of the simulation. Now let's move on to RGRG coupling platform validation problems. Our first benchmark is Tersagis, which is one-dimensional consolidation problem. It's a classic test used to validate numerical coupling methods. The setup is simple. A vertical column of fully saturated material and axial load is applied at the top. The lateral displacements are fixed, and fluid is allowed to drain only through top boundary. This causes gradual consolidation of the column as fluid pressure dissipates. So we tested three cases. The first one is an isotropic consolidation. So we can see the section of the results of the Tersagis problem while I'm explaining. So the anisotropic consolidation here, the material is homogeneous and isotropic, saturated with a compressible fluid. A constant load is applied, and the fluid drains through a producer well at the top. As you can see the results, the two plots, pressure and versus time, and settlement versus time. The pore pressure evolution and subsurface settlement show excellent agreement with analytical solutions. The pore pressure was captured in 1, 2, 3, 4 in 4 monitoring points in different positions in the vertical column. So the second case is an isotropic consolidation. In this case, we studied how directional differences in material properties affect consolidation. This is known as transverse isotropy, a condition where the rock behaves the same in one plane, such as the horizontal bearing plane, but differently in the vertical direction. For example, the rock may deform more easily along horizontal layers than vertically, due to natural depositional structures. For capturing this, we set different values for Poisson's ratio in the vertical and horizontal direction, while keeping Jones modulus equal in all orientations. So, as you can see in the plots, pressure against time and settlement against time, the numerical result for pore pressure dissipation and surface settlement show excellent agreement with the analytical solutions Developed by Cui and co-authors in 1996, this confirms that our model can correctly simulate the influence of anisotropy, which is an important factor in real geological formations where layering and fractures strongly control fluid flow and deformations. The third case for this benchmark is thermal consolidation. We included thermal effects. A heater at the top raised the temperature by 50 degrees, inducing thermal stresses, pore pressure increase, and surface heaving. Over time, as temperature and fluid dissipated through the surface, the model reproduced the decoupled thermoporoelastic behavior. As you can see in the plots, temperature against time, pressure against time, and heaving against time, the results aligned well with analytical predictions. In summary, these three benchmark cases, isotropic, anisotropic, and thermal consolidation, demonstrated that our simulation platform can reliably capture the coupled hydromechanical and thermo-hydromechanical behavior of porous media. Now let's talk about the second benchmark problem, which is the traditional Mandel's problem. Assumes normally isotropy material properties. However, in real rocks like shales, properties often vary with direction. To account for this, we simulate transversely isotropic porous media, where the rock behaves differently along the vertical axis compared to horizontal plane. This reflects the effect of layering of structural features in natural formations. For our simulation, we discretize the layer into small cubic elements, as you can see in the picture of the geometry. The rigid plateaus are modeled using a servo control mechanism which adjusts the vertical velocities at the top and at the bottom boundaries to maintain a constant applied load. Fluid drainage is allowed through wells along the lateral boundaries. For this case, we analyze 5 cases. The first one, baseline horizontal and isotropy. So meaning the isotropy plane is horizontal, representing the layered rock. The second case, incompressible solid grains. The solid skeleton is assumed incompressible, increasing biocoefficients and affecting pressure buildup. The third, reduced solid stiffness. The solid matrix is half as stiff as in the base case, showing how weaker rocks deform under load. The fourth is the vertical plane of isotropy. The isotropy plane is rotated vertically, illustrating how layer orientation affects stress and displacement. And the fifth case, it was 45-degree rotation of isotropy plane, producing complex rhombohedral deformation that cannot be solved analytically. So as we can see in the plots that we have in the results sections, these results from the simulation show excellent agreement with analytical solution where the analytical solution was available, but also provide new insight where no closed forms analytical solution exists, like the fifth case, which is 45-degree rotation of isotropy plane. So the Mandel's problem also demonstrated the ability of our simulation platform to accurately capture an isotropy, material stiffness variation, and orientation effects on coupled poromechanical behavior, critical for modeling real geological formations. So this is the end of the presentation. Thank you for your attention.